Good morning student, myself Melissa Akla, and in our subject structure analysis part 1, today we discuss the topic strain energy, and in today's session we derive two derivation. First is due to impact load and second is due to shear loading, or we can say that axial loading. Okay, now our first derivation is strain energy due to impact loading, and for that here I take a three figure. In this first figure, we can see that this load P is fall on this given bar at height h. Okay, and this h means load is act as an impact load, because here given load P is apply on this given bar at a given height, and if height is given in data, that means this is the simply case of impact load. Okay, and because of this impact load, bar is deform, and this deformation is delta L. And according to this application of load, two figure, first figure is our load deformation diagram and second figure is our resistance deformation diagram, because this is the first case of work done and this is the second case of work stored. And in first case, load P apply at height h on given bar. So P h, and because of this height, deformation will be occur in bar, that is delta L. So load deformation, it is in form of height h plus delta L, work done. And second, this is our resistance deformation diagram, and this resistance deformation diagram is always in average, that means in form of triangle. Resistance deformation diagram R into delta L. Okay, now we compare this work done on the bar is equal to force into deformation. That means force is equal to P and deformation on the bar is equal to H plus delta L. Now in first derivation of gradual load, we find out value of delta L, and this delta L is equal to sigma L by E, because ultimate delta L is equal to PL by A, and this PL by LAE we can write sigma L by E also. Okay, now P is equal to H plus delta L is equal to sigma L by E. Put this value here. Work stored in the bar is equal to 1/2 R into delta L, and this is our strain energy. From this 1/2 R into delta L, we already proved that this is our strain energy, 1/2 sigma square divided by twice E into volume. Okay, sigma is equal to stress, E is equal to Young's modulus, V is equal to volume. Now we compare work done on bar is equal to work stored or strain energy. That means P H plus delta L is equal to sigma square into volume divided by 2 into Young's modulus. Okay, now here I compare this work done on bar with the work stored. Okay, now sigma square twice C into area into length, this is our volume, right, area into length, PH plus delta L. Now value of this delta L is equal to sigma L by E, PH plus sigma L by E. Clear? Now sigma square twice C into volume, volume means our area into length, and multiply this term PH, P sigma L by E, P into H, then P sigma L by E. Now sigma square AL by AE, and shift this term from right to left, it is converted into minus sigma PL by E minus PH into equal to 0. Now multiply both side by 2E by AL. Okay, here I continue this equation. If I multiply this equation, AL by, okay, first write down here sigma square and AL by 2E, this is multiplied by 2E, write down here 2E by AL minus sigma PL by E, and multiply by 2E by AL. Okay, and our minus PH into term 2E by AL is equal to 0. Now what? This term is cancelled here, Okay, so remaining term is sigma square. In second term, E is cancelled. Okay, so and L is also cancelled. So remaining term is 2p sigma by A, and here 2ph E divide by A area into length is equal to 0. Now next, sigma square minus 2p sigma divide by A, and I shifted this term on right hand side. It is converted into positive 2phe by Al. Now sigma square, I add 2p sigma divide by area. Okay, here I add p square and a square on both left and right side. Okay, p square then a square plus 2phe divided by al. Now here look at this. This is the sigma minus p by whole square. Okay, a minus b whole square. That means sigma minus p by whole square, and this term is p square divided by a square plus 2phe by al. Now if I make a sigma as a subject, then sigma is equal to, this square will be in opposite side converted into under root, and this minus p by is positive. So p by a plus under root of p square divided by a square plus 2eph by al. Clear? Okay, here I simplify this term. After multiplying by this both side, our final equation of this sigma is equal to p by a plus under root of p square a square plus 2eph by al. This is the stress due to impact load. Okay, here our equation is complete. Now next we derive strain energy due to shear loading. Okay, in this derivation, here I take a one block, and in this block our ABCD block is given, and AD edge is fixed, and this BC edge is free, and this BC edge is subjected to load P, and this load P is act as a gradually, okay, but parallel to the box. That means shear loading. Okay, if any load is subjected parallel to the plane, it is ultimately our axial load, our shear load. And here we prove that strain energy U is equal to tau square divided by 2g into volume. Okay, this is our final derivation that we prove here. Okay, tau is equal to our shear stress, g is equal to our shear modulus or modulus of rigidity, and v is equal to volume. Okay, this block is subjected to uniform shear stress. Okay, and this uniform shear stress in clockwise direction, and because of this, here strain energy induced in this block, and we find out this value of this strain energy due to this shear loading. Okay, now one by one. Consider a square block ABCD, and length of this block is equal to L. Okay, and edge AD and this edge BC. Okay, edge AD is fixed and this edge BC is equal to free, and face BC is free and edge AD is fixed. Section ABCD, this ABCD is deformed as a B1, C1 and D due to this load P and this shear stress tau. Okay, this shear stress tau is act angle phi through in this block. Again I am repeating you, HAD is fixed, HBC is free, and this load act in HBC. Because of this our block is deformed A, B1, C1, D, and this deformation it is in term of phi, that means shear strain, and this deformation is A, B1, C1, D, and this deformation is through angle phi. Okay, here phi is equal to shear strain. We find out value of this shear strain. Tan phi is equal to this deformation BB1 divide by this length of block is equal to L, because ultimate this is our square block and length of this block is L, all side are L, okay, BB1 by L, but this deformation is very small, so we can here write tan phi as a phi. So tan phi is equal to phi is equal to BB1 divided by L. This phi is equal to this BB1 divided by length, and this is our shear strain. Okay, first equation. Now force P act on this edge BC. Okay, look at this. This force P is act on this edge BC. Ultimate, it is converted into stress. If I want to find out value of force, force is equal to stress into area. Stress, that means our shear stress, and area of block is equal to BC side and vertical side L, BC into L. Here P load is applied as a gradually, okay, and gradual load is again act as a average load that we discussed in first derivation. Okay, so it is act as average P by 2, and BB1 is equal to phi into L. G is equal to our shear modulus, and shear modulus is the ratio of shear stress to shear strain, and BC into L, this is the area of our block, okay, area of block, that means one side BC and length BC into L, okay, and load is average. Now this relation we use. Now load P is applied as a gradually, okay, on given bar, given block. U is equal to 1/2 P into delta L, and this delta L nothing but that is our deformation of given block, and this deformation is BB1, and force P, here we find out value of this force P is equal to stress into area, and area of this block is equal to BC into length L. Put this value 1/2 tau BC into L, and BB1 is equal to our deformation, and that is phi. Okay, now 1/2 tau BC into L, and this BB1, value of this BB1 is equal to shear strain into length, okay, phi into L. Now 1/2 tau, and this BC into L is nothing but that is area, okay, BC into L is nothing but that is our area of block, right here A, and phi into L, phi. Here shear modulus is the ratio of shear stress to shear strain. If I make subject as a phi, then phi shear strain is equal to tau by G. Put here tau by G. Now tau into tau is equal to tau square, 2G in denominator, area into length is equal to volume. So strain energy due to shear loading or axial loading on given block is equal to tau square into volume divided by this 2G. Tau is equal to shear stress, G is equal to shear modulus, V is equal to volume, and U is equal to strain energy. This is our final derivation of strain energy due to axial loading or shear loading. Okay, in next session we derive strain energy due to bending and second torsion. Just now we stop here. Okay, use here.